Okay, so in this video, we will consider the first three basic operations on matrices. That is matrix addition, matrix subtraction, and scalar multiplication. How can we multiply a matrix by a real number? Let's start with matrix addition. And you will see it is a very simple operation, but we can only add matrices of the same size because we're simply going to add their corresponding entries. Suppose I take the matrix 1, 2, 3, 4, and I say plus the matrix -5, 8, 9, 7. Well, this is a 2 by 2 matrix, this is a 2 by 2 matrix. The result can be performed. We can add these two matrices. The new matrix will still be a 2 by 2 matrix, and we find the entries of the new matrix simply by adding corresponding entries. So the entry 1, 1 with the entry 1, 1. So we get 1 plus -5, -4. The entry 1, 2 with the entry 1, 2, 2 plus 8, +10. The entry 2, 1 with the entry 2, 1, 3 plus 9, 12. And finally the entry 2, 2 plus the entry 2, 2, 4 plus 7, 11. So if you call this matrix A, being a 2 by 2 matrix, this matrix B, another 2 by 2 matrix, this matrix is obviously A plus B. So when we add matrices, we simply add corresponding entries. Now think of why we need to have the same size. What if we tried to add the following two matrices? So 1, 2, 3, 4, plus, say, the matrix -5, 8, 9, 7, 0, 1. Then there's a problem. This is a 2 by 2 matrix. This is a 2 by 3 matrix. So the first question is, what's the size of the new matrix? This is a 2 by 2. This is a 2 by 3. And we're going to add 1 with -5, 2 with 8, 3 with 9, 4 with 7. But what about these two? There's nothing here to be added to these two entries. And so for that reason, the addition of these two matrices is not defined. We can only add matrices of the same size because we're adding corresponding entries. What about matrix subtraction? Let's take a 3 by 3 matrix. 1, 2, 3, 4, -5, 5, 6, 1, -2, minus another 3 by 3 matrix. Let's go with 7, 8, 9, 1, 1, 1, 2, 3, -2. This is a 3 by 3 matrix. This is also a 3 by 3. So we can perform the subtraction. The resulting matrix will also be a 3 by 3. And of course we perform addition, or I should say subtraction of matrices, just as addition. When we add matrices, we add the corresponding entries. When we subtract matrices, we subtract corresponding entries. So the entry here will be 1 minus 7, -6. The entry here will be 2 minus 8, -6. The entry here will be 3 minus 9, -6. Let's keep going. 4 minus 1, +3. -5, -1, -6. 5 minus 1, 4. 6 minus 2, 4. 1, -3, -2. -2, -2. Let's -2 plus 2, which is 0. So you see matrix addition and subtraction is very simple. We either add or subtract corresponding entries. The only thing is we can only add and subtract matrices of the same size. So let's write this using our entry notation for matrices. So suppose we let A and B be matrices of the same size, so they're both, say, M by N matrix. Then As we have just seen, when we add or subtract the two matrices, the new one still has the same size. So if A and B are m by n matrices, then A plus or minus B will still be an m by n matrix. The size does not change. And how do we find the entries of our new matrix? Well, if you think of it, if you take any entry of the new matrix, you simply add or subtract corresponding entries. So, if you look at this one, say, and this is your matrix A, this is your matrix B, this is your matrix now A plus B, A minus B, sorry. And you see if we ask, how did we obtain the entry in A minus B in the second row, second column? Well, we took the entry of A in the second row, second column, and we subtracted the entry in B in the same position. So you see, when we ask, how do we find the entries of A minus B? Well, we take the corresponding entry in A minus the corresponding entry in B. Same thing if you had an addition. So, how do we find the entry of our new matrix A plus B or A minus B in the ith row, jth column? We simply take the entry in A in the ith row, jth column, and we add to that or subtract, depending on if we're adding or subtracting, the corresponding entry in B. So the entry in matrix B in the ith row, jth column. And that's how we can write this very concisely. In words, all we're saying is that we add or subtract matrices by adding or subtracting the corresponding entries. Let's look at one simple example of a subtraction, and then we'll define a very simple but very important matrix. What if we did A minus A? What if the matrix A was 1, 2, 3, 4, and we do A minus itself? Well, the result will be a 2 by 2 matrix, and we're subtracting the same entries every time. 1 with 1, 2 with 2, 3 with 3, 4 with 4, and the result is a matrix where every entry is equal to 0. And now there's a very natural question, is what name should we give this matrix? Well, if you think of it, we're doing A minus A. So think of real numbers. If you do A minus A, the result should be 0. Well, now we don't have the 0 real number, but a matrix of 0. So this will be called the 0 matrix. In our case, this is a 0, 2 by 2 matrix. So in general, if you say the 0 m by n matrix, it is an m by n matrix where every entry is equal to 0. So for example, this is the 0. Well, 1, 2, 3, 4 rows, 2 columns, so it is the 0, 4 by 2 matrix, and so on. That's a very natural definition. The 0 m by n matrix is an m by n matrix where every entry is equal to 0. So this takes care of matrix addition and matrix subtraction. Now what about multiplying a matrix by a real number? Let's see how we can naturally define this if we only look at matrix addition. Let's take this to be A again, and now let's do A plus A. The result will be a 2 by 2 matrix again, and if we add A with A, we'll get 1 plus 1, 2, 2 plus 2, 4, 3 plus 3, 6, 4 plus 4, 8. Let's do A plus A plus A. Well, if you think of it, we already have A plus A, so we add to that A once again. So we'll get 1 plus 2, 3, 2 plus 4, 6, 3 plus 6, 9, 4 plus 8, 12. And now let's ask, can we view this addition, and this one, instead of as an addition of A with A and A with A with A, as simply a multiple of A? Think of A as a real number for a second. If you think of A as a real number, naturally, you would write A plus A as 2 times A. And naturally, you would write A plus A plus A as 3 times A. Let's see if this makes sense. We're going to ask, how do we obtain these two matrices from 2 times A and 3 times A? The matrix A is 1, 2, 3, 4. The matrix A again is 1, 2, 3, 4. And so you see, how can we multiply a matrix by a real number so that the result makes sense? Because if you do 2 times A, naturally, you should obtain A plus A. If you do 3 times A, naturally, you should obtain A plus A plus A. So that our definition of multiplying a matrix by a real number is consistent with our definition of matrix addition. Well, if you look here, if you do 2 times 1, it's 2. If you do 2 times 2, it's 4. 2 times 3 is 6. 2 times 4 is 8. If you do 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. So you see, quite simply, when you multiply a matrix by a real number, you simply multiply every entry of the matrix by the given real number. And that's our definition of scalar multiplication. And it is the only natural one because it extends our definition of matrix addition. So let's define this. So we'll let A be an arbitrary rectangular matrix, and we'll take K to be our scalar, our real number. So A is any m by n matrix, and let's take K to be some real number. Any real number. Then we have, see, now we can define a new matrix K times A, and we simply multiply every entry of matrix A by the real number K. So first observation, the matrix will still have the same size as A. This will still be an m by n matrix. The size does not change. And how can we write very concisely that to obtain an entry of Ka, we simply multiply the corresponding entry of A by K? Well, think of it. We ask, how do we find an entry of the new matrix Ka, say in the ith row, jth column? Well, because we multiply the entries of A by K, we will simply take the corresponding entry of A. So take the entry in A in the ith row, jth column, and multiply this entry by K, and you will get the entry of Ka in the ith row, jth column. So we simply multiply each entry of A by the real number K. Let's look at one simple example where K is any K. Let's do K times the matrix 1, 2, 3, negative 4, 6, 9. So now A is a 3 by 2 matrix. And again, as we have said, the matrix will have the new matrix K times A is of the same size, and we simply multiply every entry of A by the real number. So we'll have K times 1 K, K times 2 2K, K times 3 3K, K times negative 4 negative 4K, 6K, and 9K. And this is now the matrix Ka. And let's see if we understand this notation. Suppose we look at the entry, say, 9K. Well, This is the entry of the matrix K times A in the third row, second column. And how did we arrive at this entry? Well, we took the entry in A in the third row, second column, in the exact same position. And to get to this entry, we simply multiply the entry of A in the third row, second column by the real number K. That's all we're saying. So when you perform a real multiple of a matrix, you simply multiply every entry of the matrix by whatever real number you have. And this is called scalar multiplication. Scalar is simply a synonym of constant, or if you prefer, a real number. So we now have seen how we can add matrices, subtract matrices, and multiply them by a real number. Let's do an example that involves two operations, addition and scalar multiplication. So what if we did 2 times the matrix 1, 2, 3, negative 1, 4, 6, plus 3 times the matrix negative 1, negative 1, 1, 3, 2, 5. Well, we can do here two things at once. We can multiply by the scalars and at the same time add. 2 times 1 plus 3 times negative 1. 2 minus 3 is negative 1. Then 2 times 2 is 4. Minus 3, positive 1. 2 times 3 is 6. Plus 3 is 9. And we have our first row. 2 times negative 1, negative 2, plus 3 times 3, 9. 2 plus negative 2 plus 9 is 7. 2 times 4, 8, plus 3 times 2, 6. 8 plus 6 is 14. And finally, 2 times 6, 12, plus 3 times 5, 15. 12 plus 15 is 27. And now we have our new matrix. If you want, you can go a little slower and compute both scalar multiplications individually. So you'll have the matrix 2, 4, 6, negative 2, 8, 12. And the other scalar multiplication, negative 3, negative 3, 3, 9, 6, 15. And then add them up. 2 minus 3, negative 1. 4 plus minus 3, 1. 6 plus 3, 9. Negative 2 plus 9, 7. 8 plus 6, 14. 12 plus 15, 27. And that's it.